3 billion years ago, if you had flown over our solar system, you would have spotted something strange. Mars wasn't red, it was blue. Oceans stretched across half its northern hemisphere. Rivers carved valleys as wide as continents. Rain fell on its plains. And not far away, Venus, the planet we call a hell today, was perhaps temperate, covered in water, bathed in light warmer than ours, but not deadly. Two living worlds, within reach. Then something broke. On Mars, a core cooled, an invisible shield switched off, and the solar wind began to erode the atmosphere, the way an eraser wipes out a pencil mark. On Venus, a runaway greenhouse effect turned the oceans to steam and the surface into a furnace. Within a few 100 million years, a blink on a cosmic scale, two potentially habitable planets became the most hostile worlds in our neighborhood. But here is the question that has haunted scientists for decades, the one that keeps engineers, biologists, physicists, and dreamers up at night. What if we could reverse that process? What if we had, today, the tools to awaken Mars, to cool Venus, to breathe a new atmosphere into a dead world and plant the seeds of life there? This is what we call terraforming, and it is no longer just science fiction. What we are going to explore together in this video is perhaps the most ambitious project the human mind has ever conceived. Greater than the pyramids, greater than the atomic bomb, greater than Apollo. We are talking about transforming an entire planet, its chemistry, its physics, its biology, so that it resembles our Earth. We are talking about creating a second home for humanity, tens of millions of kilometers from here. We are going to see how scientists envision doing it, what obstacles seem almost insurmountable, what new ideas have recently changed the game, and above all, how long it would actually take. If you are watching this video and you enjoy topics that make your head spin, subscribe to the channel and leave a like. It helps us enormously to keep doing this work. And in the description, you will find a link if you would like to support the channel with a donation. Every contribution allows us to produce richer, more thoroughly researched videos. Tell us in the comments which city you are watching from and what time it is where you are right now. So let us start at the very beginning with a word. A single word slipped into a science fiction magazine one morning in 1942 that would eventually find its way into the laboratories of NASA. In July 1942, an American writer by the name of Jack Williamson published a short story in the magazine Astounding Science Fiction. The title of the story was Collision Orbit. The story itself would not be remembered, but within its pages, Williamson used for the first time a verb that had never existed until that precise moment: terraforming. He used it in passing, almost as a given, to describe the transformation of an asteroid into a habitable world. A word built from the Latin terra, earth, and the verb to form, to shape, to terraform, to shape in the image of Earth. That word would make its way quietly for 20 years, until a 26-year-old astronomer named Carl Sagan decided to take the idea seriously. It was 1961. The Cold War was at its height. The first rockets were piercing the atmosphere, and no one yet knew with certainty what lay beneath the thick clouds of Venus. Sagan published in the journal Science an article that would astonish the scientific community. He proposed, with rigorous methodology, a method for modifying the atmosphere of Venus, not in a novel, in an academic journal, with equations, with data. For the first time in history, a credible scientist treated terraforming as a genuine engineering problem. His idea was, in hindsight, flawed. He suggested seeding the Venusian clouds with photosynthetic algae to convert carbon dioxide into oxygen, not yet knowing how crushing the atmosphere of Venus truly was. But the essential thing was not the solution. The essential thing was the question. Sagan had just opened a door. In the decades that followed, NASA itself organized conferences on planetary transformation. Engineers, biologists, and physicists gathered to think seriously about what still looked like gentle madness. In 1976, the agency even used an official term, planetary ecosynthesis, to describe this work. Scientists searched for their own terminology. In 1995, the term ecogenesis was proposed. In 2008, the term biospherization entered official dictionaries, defined as the transformation of a planet to create conditions similar to Earth's biosphere. But behind those scholarly words, there is a very concrete reality. Over 60 years, what had been the daydream of a pulp fiction author became a legitimate field of research, studied at the world's leading universities, debated in the most serious scientific journals, and taken very seriously by billionaires building rockets in their Texas backyards. A word invented in a forgotten short story planted a seed in the human imagination, and that seed today is beginning to grow. Before going further, we need to agree on what terraforming a planet actually means, because the word is often misunderstood, and the confusion can lead to unrealistic expectations in both directions. Terraforming, in its most precise definition, is the process by which one deliberately modifies the atmosphere, temperature, surface, and ecology of a celestial body to make it resemble Earth and be habitable by human beings. Not simply habitable for microbes, not simply livable under a glass dome, habitable autonomously, in the open air, without a spacesuit, without special survival equipment. That is a crucial distinction. Building a lunar base under a pressurized dome is not terraforming. Growing vegetables in a Martian greenhouse is not terraforming. To terraform a planet is to change the planet itself, its fundamental chemistry, its atmospheric dynamics, its ability to retain heat and protect life from radiation, until a child can run outside, breathe the air, feel rain fall on their skin. This project is also distinct from a parallel concept that scientists call pantropia, from the Greek pan, meaning all, and tropia, meaning transformation. Pantropia is the inverse idea. Rather than modifying the planet to suit humans, one modifies humans to suit the planet. Genetically engineering human beings to withstand extreme temperatures, different gravity, a less dense atmosphere. It is an approach that science fiction has explored extensively, and that synthetic biology is beginning to touch concretely. In practice, these two paths are not mutually exclusive. Some researchers envision a combination of both to accelerate colonization. But even before full terraforming, scientists speak of a preliminary stage they call ekopoiesis, a Greek word that literally means the creation of the conditions necessary for life. Ekopoiesis is the seeding of a planet with pioneer organisms, bacteria, algae, cyanobacteria capable of surviving in extreme conditions and beginning, very slowly, to modify their environment. These organisms work like invisible builders. They produce oxygen, they break down rocks, they create the first organic deposits that may one day nourish more complex forms of life. Ekopoiesis is preparing the ground. Terraforming is the house built upon it. Why is this project of a complexity without equal in the history of human engineering? Because it involves simultaneously modifying dozens of interdependent systems on a planetary scale, over timescales that exceed the lifespan of a civilization. Warming or cooling an atmosphere takes centuries. Creating a functioning water cycle takes millennia. Generating enough oxygen for a human being to breathe freely can take hundreds of millennia. And all of this must hold together, stabilize, withstand disruptions, solar storms, orbital variations, unforeseen chemical reactions. Building a pyramid takes 20 years and thousands of workers. Terraforming a planet is building a pyramid the size of a world and keeping it in balance while the entire universe tries to bring it down. It is the most ambitious, the longest, and perhaps the most necessary engineering that humanity has ever imagined. And to understand why it is necessary, to understand what we are trying to recreate, we must first understand what we almost had. We need to talk about Mars. Not today's Mars, cold and dead, the Mars that came before. Imagine you could travel back in time to 4 billion years ago. You land on Mars, or rather, on what will become Mars, and what you see bears no resemblance to the ochre, irradiated desert that rovers roam today. You see water. A lot of water. The northern hemisphere is covered by a shallow ocean, perhaps 100 meters deep on average, but stretching across millions of square kilometers. Rivers drain the southern highlands toward this ocean, rivers wider than the Amazon, which have carved into the rock valley systems we can still see today from orbit. It rains. Snow falls on volcanic summits. Lakes pool in craters. The atmosphere is dense, laden with carbon dioxide, unbreathable for us, but thick, protective, capable of keeping liquid water on the surface. The Martian sky may be a pale blue, slightly pink at the horizon, under a sun a little farther than ours, but still warm. This is not romantic speculation. These are solid, scientific conclusions, built on decades of data. The rover's spirit, opportunity, curiosity, and perseverance have all found evidence of this aquatic Mars, clay minerals that only form in the presence of persistent liquid water, sulfate deposits that resemble the remains of an evaporated sea, hematite concretions, small iron-rich spheres that geologists nicknamed Martian blueberries, which form in standing water. The Curiosity rover explored Gale Crater, which was once a calm lake for millions of years. Perseverance is currently roving a fossilized river delta in Jezero Crater. And more recently, in 2021, a Franco-American collaboration published work supporting the hypothesis of a Mars with a cold but humid climate as recently as around 3 billion years ago. One of the researchers from that study summed it up in a single sentence. If you could have walked on that Mars wearing a spacesuit for the oxygen, you would have found the pressure, the clouds, the liquid water, the rain, and the snow. All of that was there, only the oxygen was missing. So what happened? How did we go from that primordial Eden to the irradiated desert of today? The answer comes down to one word: magnetosphere. Earth possesses a giant magnetic field, generated by the movements of its molten iron core. Picture an invisible shield enveloping the entire planet, deflecting the charged particles that continuously pour from the sun, what we call the solar wind. That shield does two crucial things. It protects the surface from lethal radiation, and it prevents the atmosphere from being literally stripped away by the particle flux. Mars also had this shield. Then it lost it. Mars is a smaller planet than Earth. Smaller means a core that cools faster, and a cooling core is a core that ceases to produce the convective movements necessary for the dynamo effect, the mechanism that generates the magnetic field. Around 3 to 4 billion years ago, the Martian core solidified. The shield switched off. What happened next, we have observed directly. NASA's MAVEN spacecraft, placed in orbit around Mars in 2014, measured the rate at which the solar wind strips particles from the Martian atmosphere today. And in 2025, a team led by Shannon Curry published the first direct evidence of an even more violent process, atmospheric sputtering, in which ions from the solar wind strike atmospheric molecules and eject them into space like billiard balls. This process, the researchers estimate, was once 4 times more intense when the sun was younger and more active. Result: Mars lost its atmosphere within a few 100 million years. Pressure dropped. Liquid water could no longer exist on the surface. Without sufficient pressure, water passes directly from solid to gas without ever becoming liquid. The oceans froze. The ice sublimated into space or buried itself underground. The average temperature plummeted, and solar radiation, now without a barrier, made the surface hostile to any complex form of life. Mars died, but it holds a memory, and in that memory, there may be a blueprint for bringing it back to life. To know whether terraforming Mars is possible, the first question to ask is simple. What do we have to work with? What is the planet's inventory? Let us start with the good news, because there is some. Mars rotates on its axis in 24 hours and 37 minutes, barely more than a terrestrial day. This is an extraordinary and welcome coincidence. It means day-night cycles comparable to our own, temperatures that do not collapse for months in total darkness, and biological rhythms that our bodies could likely adapt to tolerate. Mars's axis of rotation is tilted at about 25 degrees relative to its orbital plane, almost identical to Earth's 23-degree tilt. There are therefore seasons on Mars: springs, summers, autumns, winters, less pronounced than ours, but recognizable. There is water on Mars, far more than was thought 30 years ago. Ice in the polar caps, thick layers several kilometers deep, ice just below the surface, across vast regions of the northern hemisphere. indications of liquid salt lakes beneath the southern polar cap. And within the rocks themselves, trapped in hydrated minerals, chemically bound water that represents a considerable reservoir. If all this water were gathered together, it would form a global ocean more than 100 meters deep. The Martian soil also contains nitrogen and argon in small proportions. There are iron oxides, silicon, calcium, magnesium, elements that plants need to grow. Gravity is 1/3 of Earth's gravity, a constraint on the human body over the long term, but one that makes launching materials from the surface easier. Now, the bad news. The Martian atmosphere is almost non-existent. It represents about 1/160th of Earth's atmospheric pressure. It is composed of nearly 95% carbon dioxide, with only traces of nitrogen, oxygen, and argon. Under these conditions, if you were to remove your spacesuit on the surface, your blood would begin to boil within seconds. Not from heat, but from the absence of pressure. And you would die from radiation, because this thin atmosphere filters almost none of the ultraviolet rays or cosmic radiation. The average surface temperature hovers around -60 degrees Celsius. In summer, near the equator, it can reach a few degrees above zero at midday. In winter, at the poles, it drops to -125. A Martian thermometer looks like a polar thermometer on Earth, from which someone has torn off all the positive degrees. And then there is the absence of a magnetosphere. That shield, extinguished billions of years ago. Without it, the Martian surface is continuously bombarded by ionizing radiation that destroys complex organic molecules and would render the surface sterile to most known forms of life. In 2018, two NASA researchers, Bruce Jakosky and Christopher Edwards, conducted a meticulous inventory of all the carbon dioxide available on Mars, in the polar caps, in the soil, in the rocks, in the minerals, to assess whether there was enough to reconstitute a viable atmosphere through simple warming. Their conclusion was stark. No. Even by mobilizing all of the planet's CO2 reserves, one would obtain an atmosphere only twice as dense as the current one, still 100 times thinner than ours. Not enough for water to remain liquid, not enough to protect against radiation, not enough to allow breathing. This result dampened a great deal of enthusiasm. It means one cannot simply heat Mars to melt its ice and naturally reconstitute an atmosphere. External resources will have to be brought in, or radically new technologies will have to be invented. Which brings us to the central question. If Martian resources are insufficient, what are the solutions? What tools has human engineering put on the table to build an atmosphere where there is virtually none left? The answers, some bold, others almost poetic in their audacity, together sketch a roadmap towards something that would look like a miracle, and that may be nothing more than a question of time and will. These solutions exist. They are bold, some appear outlandish at first glance, but all of them are grounded in real physics. Here is the Terraformer's toolkit. The first idea that appears in nearly every serious study is the giant orbital mirror. Imagine a reflective panel, 125 kilometers in radius. Not glass, but a thin sheet of aluminum deployed in space, placed in orbit around Mars to concentrate sunlight on the southern polar cap. The southern cap of Mars contains a layer of frozen carbon dioxide on top of the water ice. If warmed, this CO2 is released into the atmosphere, thickening the gaseous blanket, amplifying the greenhouse effect, which warms the planet further, which releases even more gas. A virtuous cycle of thermal escalation that engineers call a positive feedback loop. Robert Zubrin, founder of the Mars Society, estimates that an initial push of a few degrees could trigger this process and let it cascade on its own. Russia's Znamya project in 1999 already tested a small 25-meter mirror in Earth orbit. The technology exists. The scale, however, is another matter entirely. The second approach, even more spectacular, involves bombarding Mars with comets or asteroids rich in ice and ammonia. Carbonaceous asteroids from the outer solar system contain enormous quantities of ammonia, a powerful greenhouse gas that also contains nitrogen, the inert gas that dilutes our terrestrial atmosphere and that Mars possesses in insufficient quantities. By carefully redirecting dozens or even hundreds of these asteroids to crash into Mars, Ideally, with the help of nuclear charges that would alter their trajectories, one could simultaneously inject heat, water, nitrogen, and greenhouse gases. Yes, the impacts would cause massive destruction in the short term, but on a planet without life, that is merely a construction inconvenience. A third avenue, closer to our current capabilities, is the industrial injection of artificial greenhouse gases. Chlorofluorocarbons, the infamous CFCs, responsible for the hole in Earth's ozone layer, are in fact greenhouse gases thousands of times more potent than carbon dioxide. On Mars, where there is no ozone layer to protect, factories could be built on the surface to continuously produce these gases and inject them into the atmosphere. Zubrin has calculated that factories running for several decades could thicken the Martian atmosphere enough to stop the most dangerous radiation and allow human beings to move around without a pressurized suit, with only an oxygen mask. That is not yet breathable air, but it is a colossal first step. The fourth idea comes from a team at Harvard, NASA's Jet Propulsion Laboratory, and the University of Edinburgh, and it was published in 2019 in Nature Astronomy. Its principle is almost poetic in its simplicity. Rather than terraforming the entire planet at once, an endeavor spanning several millennia, why not start by creating oases, small habitable zones protected by a remarkable material, silica aerogel. Silica aerogel is the lightest solid in existence. It is composed of nearly 98% air, trapped within a network of silicon dioxide fibers at the nanoscale. It looks like solidified smoke, and it possesses three simultaneous properties that make it an almost miraculous material for locally terraforming Mars. It allows visible light through to enable photosynthesis. It blocks dangerous ultraviolet rays, and it traps heat beneath it, like a glass blanket. The researchers demonstrated in the laboratory that a layer of 2 to 3 centimeters of aerogel is sufficient to raise the temperature of the ground beneath it by more than 50 degrees Celsius, enough to maintain liquid water on the surface in Mars's most favorable regions, year-round. After 20 years of continuous presence, the habitable zone beneath this shield would extend to a depth of 15 meters. Domes covered with aerogel could create environments where plants could grow, with almost no maintenance. It is not yet green Mars, but it is the beginning. A fifth approach, even more recent, explores atmospheric nanoparticles. Researchers have proposed manufacturing artificial dust particles in the shape of microscopic rods, approximately 9 microns long, roughly the size of some terrestrial pollution particles, and continuously releasing them into the Martian atmosphere. These nanoparticles are designed to block outgoing thermal infrared radiation while allowing solar light to enter, the perfect greenhouse effect. Calculations suggest that a continuous release of these particles could raise the global temperature by more than 10 degrees Celsius within just a few months. And if one wanted to cancel the effect, it would only be necessary to stop production. The particles would settle on their own within a few years. Finally, to coordinate all of this, engineers envision fleets of autonomous robots deployed on the surface, drills, atmosphere mixers, portable bioreactors that would prepare the ground, build habitats, produce useful gases locally, and could be preceded or even accompanied by a silent army of biological pioneers, living organisms, chosen or engineered to survive in conditions that nothing on Earth has ever inhabited before. But even before discussing these pioneer organisms, there remains a problem that none of these tools resolves. A fundamental problem that stands like a wall before the entire toolkit. If we build an atmosphere on Mars and have not solved the solar wind problem, that atmosphere will leave, slowly, inexorably. It will evaporate into space, as it has already done once before. This is the cruel paradox at the heart of every discussion about terraforming Mars. You spend centuries building an atmosphere, you warm the planet, you release the gases, you send organisms, you create a water cycle, and all the while, the solar wind keeps blowing. It keeps stripping away, molecule by molecule, particle by particle, the gaseous blanket it took you so long to build. On a human timescale, this is not visible. Today we lose a few hundred tons of Martian atmosphere per year to the solar wind, which seems negligible, but on the scale of millennia, it is a mortal hemorrhage. Over millions of years, a reconstituted atmosphere without magnetic protection would eventually erode completely, just as it did several billion years ago. Terraforming Mars without recreating its magnetic shield is like filling a bathtub with the drain left open. How does one recreate a magnetic field for an entire planet? On Earth, this field is produced by the dynamo effect. The liquid iron core of our planet, kept molten by internal heat accumulated since the formation of the solar system, generates electrical currents that in turn produce a global magnetic field. Mars has lost that internal heat. Its core cooled, solidified, and the dynamo effect switched off. One could, theoretically, try to restart the core by injecting energy into it, but the quantities required would be so colossal that the idea exceeds any conceivable engineering for now. So scientists thought differently. If the magnetic field cannot be created from within the planet, why not create it from outside? In 2017, at a NASA workshop titled Planetary Science Vision 2050, Dr. Jim Green, then director of the agency's Planetary Science Division, presented an idea that generated significant discussion: placing an artificial magnetic dipole at the L1 Lagrange point between the Sun and Mars. The L1 Lagrange point is the position in space where the gravitational poles of the Sun and Mars exactly balance. An object placed there remains indefinitely, as if suspended between the two bodies. A powerful magnet at that precise point would deflect the solar wind before it even reached Mars, creating a kind of magnetic umbrella for the entire planet. Simulations carried out by NASA's Community Coordinated Modeling Center showed that this dipole shield could effectively reduce atmospheric erosion to a manageable level. According to the predictions, with this shield in place and the Martian atmosphere thickening naturally through warming, the global temperature of Mars could increase by several degrees within a few decades, enough to trigger partial melting of the polar caps and atmospheric thickening without any additional direct intervention. Green himself acknowledged that the idea might seem fanciful, but he insisted on a crucial point. Research into creating miniature magnetospheres to protect astronauts and spacecraft from radiation is already underway. The small-scale technology exists. The challenge is scaling it up to a planetary level. Another approach, even more creative, uses a resource Mars already possesses: its moon, Phobos. Phobos is a small, irregular moon, probably a captured asteroid, which orbits so close to Mars that it completes a full orbit in just 8 hours. A team of researchers from NASA, the RAL Space Laboratory, and Princeton University proposed ionizing particles from the surface of Phobos and accelerating them to form a plasma torus around Mars, a ring of ionized gas that, carrying an electric current, would generate a protective magnetic field. The phenomenon already exists naturally in our solar system. Jupiter's magnetic field creates exactly this type of plasma torus around its moon Io, carrying electrical currents of a power that exceeds anything humanity has ever produced. The technology to realize this vision at Martian scale does not yet exist, but the physical principle is sound, and researchers are confident that it falls within the realm of future engineering rather than theoretical impossibility. What is certain is that solving the magnetic problem is a prerequisite for any lasting terraforming. There is no point building an atmosphere if it escapes, and no point sending living organisms if radiation destroys them before they can do their work. That work, the work of living organisms, those biological pioneers that would come first, before humans, before domes, before cities, may represent the most fascinating key in the entire equation. Before the machines, before the mirrors and the redirected comets, there is something that life has proven to do better than any human engineering: transform hostile environments. Earth itself is the proof. 2.5 billion years ago, our atmosphere contained virtually no oxygen. It was bacterial photosynthesis, billions of microscopic cyanobacteria, that gradually filled the air with the gas we breathe today. It was not a planned project. It was simply life doing what life does: multiply, consume, transform, excrete. Biological terraforming follows the same principle, but deliberately guided. Ecopoiesis, that first phase of terraforming, in which a planet is seeded with pioneer organisms, would rely first on bacteria, but not just any bacteria. bacteria already tested at the very limits of what life can tolerate. The cyanobacterium Croococcidiopsis thermalis is an emblematic case. This microscopic organism has the ability to photosynthesize under extremely low light conditions. It survives within translucent rocks, in arid deserts, in glacial environments. It has even been tested directly in space. Samples placed outside the International Space Station, exposed to the vacuum of space, unfiltered solar radiation, and extreme temperature fluctuations, survived that exposure. They did not thrive, but they survived. Scientists call this kind of organism an extremophile, forms of life that have made their home in the most hostile environments on Earth, and that give astrobiologists the intuition that life is far more robust than we imagine. In the dry valleys of Antarctica, areas so cold, so dry, so exposed to ultraviolet rays that they resemble the Martian surface more than anywhere else on Earth, microbial communities live within the first few millimeters of translucent rocks, using the light that filters through to photosynthesize, protected by the rock itself. In the Atacama Desert in Chile, the driest place on the planet, bacteria have developed mechanisms to extract moisture from morning fogs. In hydrothermal vents, others thrive in boiling, acidic waters. Why is all of this relevant to Mars? Because if organisms designed to survive in these conditions were transported to Mars and deposited in the most favorable zones, equatorial valleys during the warmest hours, beneath a protective aerogel layer, in zones where liquid water can temporarily exist, they could begin to change their environment, very slowly, but irreversibly. A cyanobacterium undergoing photosynthesis produces oxygen. It also breaks down rocks, releases minerals, creates organic matter. Its dead descendants accumulate, forming the first layers of organic soil. Other organisms can then take hold: algae, mosses, lichens. Each generation prepares the ground for the next. This is exactly what happened on Earth during the colonization of bare rock by life, after glaciations, after volcanic eruptions that sterilized entire swaths of continents. But natural extremophiles have their limits. They evolved to adapt to terrestrial conditions, even extreme ones. Mars presents additional challenges. Levels of perchlorates in the soil that are toxic to most known organisms, different gravity, more intense radiation, a unique atmospheric chemical composition. This is where synthetic biology comes in. Researchers are today working on designing custom-built organisms for terraforming. Cyanobacteria modified to withstand Martian perchlorates, bacteria capable of extracting nitrogen directly from the soil, organisms that would produce specific greenhouse gases rather than simply oxygen. Synthetic biology allows one to take an existing organism and precisely insert the genes needed to give it new resistances or new functions, like a programmer modifying the code of a piece of software to give it a new capability. This is not science fiction. University teams are already working on these projects, funded in part by NASA. Results are still preliminary, the obstacles numerous, the ethical questions considerable, but the direction has been set. With all these tools, mirrors, comets, gases, aerogels, nanoparticles, robots, and microorganisms, we can now ask the question everyone wants answered. If we started tomorrow, how long would all of this actually take? It is the question asked of engineers at Mars Society conferences, the one Carl Sagan asked himself at night in his Cornell office, the one Elon Musk diplomatically sidesteps at his presentations. And the answer, depending on who you ask and what technology you assume to be available, spans a vertiginous range, from a few centuries to hundreds of millennia. Let us try to be concrete. Let us unfold the most technologically optimistic, plausible scenario. Not the science fiction film scenario, but one that can be defended with serious physics. The first few decades would be devoted to laying the foundations. The magnetic shield would be deployed at the L1 Lagrange point. The first orbital mirrors would be sent to concentrate sunlight on the southern polar cap and begin releasing the frozen CO2. The first surface factories producing greenhouse gases would be installed. The first waves of pioneer organisms would be launched, sheltered under aerogel domes in the most favorable equatorial regions. The results would be almost imperceptible on a human scale. Atmospheric pressure would begin to rise, by a tiny fraction but upward. global temperature might increase by a few degrees. After a century, according to the most optimistic estimates from NASA teams, the situation would begin to change visibly. The partial melting of the polar caps would have released enough CO2 to significantly thicken the atmosphere. Temperatures at equatorial latitudes might reach values that are negative, but close to zero. It would begin to rain sporadically in the warmest zones. Not much, but liquid water, on the surface, visible. The first human colonies would be established under pressurized domes, but residents could go outside with an oxygen mask rather than a full suit. That is an immense transformation compared to today. 500 years into the process, the atmosphere would be noticeably denser. The water cycle would operate in a primitive fashion. Clouds would form, rains would fall regularly at certain latitudes. The pioneer organisms would have colonized broad areas, creating the first green patches against a backdrop still largely red and brown. These organisms would slowly convert CO2 into oxygen. Not enough to breathe, but enough for the atmosphere to begin changing composition. Human colonies would have expanded. Habitats would have grown into ever larger domes. Children would have been born on Mars, having never set foot on Earth. Between 500 and 1,000 years, plant life, mosses, ferns, genetically adapted pioneer plants, would have begun to cover the most favorable zones. The first primitive forests, sparse and spread out, would begin to appear in the equatorial valleys. The oxygen content of the atmosphere would increase, slowly, with each generation of plants. The outside temperature would still be cold, perhaps negative at night, slightly positive at midday near the equator, but the process would clearly be underway, and clearly irreversible. That is the reasonably optimistic picture. Now, the hard reality. Reaching an atmosphere truly breathable by humans without equipment, the real ultimate goal of terraforming, could take between 1,000 and 100,000 years. Some conservative calculations speak of even longer timescales. Because oxygen must reach a sufficient concentration within an atmosphere that must itself have sufficient pressure. Nitrogen, the inert gas indispensable to life, that makes up 4/5 of our air, is scarce on Mars and would have to be imported in gigantic quantities. And even if biology and technology work together without interruption, atmospheric reactions on a planetary scale follow their own rhythms, indifferent to human impatience. Frank Montmessin, research director at the CNRS, working on planetary atmospheres, put it plainly. At this time, the complete terraforming of Mars is entirely impossible. We do not have the technological means. It is a project that can only be contemplated over the centuries to come, and with technologies we have not yet invented. What this means in practice is that terraforming is not a project humanity would see completed. It is a project humanity would begin. A project passed from generation to generation, like a cathedral that those who start building know they will never see finished, but build anyway, because the idea is worth it. The longest continuous project in human history, the construction of some Gothic cathedrals, lasted a few centuries. A complete terraforming could require 1,000 times more. But Mars is not the only candidate. 30 million kilometers in the other direction, there is a planet that poses even more dizzying challenges, yet offers opportunities that few imagine. Venus is the greatest astronomical lie in the solar system. Seen from Earth, it shines like the brightest star in the sky, brighter than anything else after the sun and the moon. It is beautiful, it is close, it is almost exactly the same size as our planet. And for centuries, astronomers imagined it might be a tropical paradise beneath its thick clouds. Then we sent probes. The first to land, Venera 7 in 1970, transmitted data for 22 minutes before being crushed and melted. What the Soviet instruments measured sent a chill through the engineers waiting for the data. A surface temperature of approximately 460 degrees Celsius, hot enough to melt lead, zinc, and tin. An atmospheric pressure equivalent to what one would feel 1 kilometer below the ocean's surface. And clouds made not of water, but of concentrated sulfuric acid. Venus is a furnace. It is crushing. It dissolves metals. The most robust Soviet probes lasted only a few hours on the surface before being destroyed by the environment. And yet, Venus is the planet scientists call Earth's twin. Same size, same mass, almost the same composition. The two planets formed at the same moment, from the same cloud of gas and dust. And the data accumulated over recent decades suggests something troubling. Venus may have resembled Earth for 2 to 3 billion years, perhaps even longer than Mars was habitable. Recent simulations indicate that its primitive surface was very similar to early Earth, with lakes, perhaps oceans, temperate conditions. Then something went wrong. The dominant hypothesis is a runaway greenhouse effect. The gradual increase in the sun's luminosity evaporated the Venusian oceans, releasing enormous quantities of water vapor into the atmosphere. And water vapor is itself a powerful greenhouse gas, which released more heat, evaporated still more water in an uncontrollable spiral. Today, Venus's atmosphere is composed of more than 96% carbon dioxide, with a pressure 90 times greater than ours. It is the greenhouse effect, pushed to its absolute extreme. Can Venus be terraformed? Technically, yes, but the challenges are of a wholly different nature than those of Mars. The first challenge is cooling. For the surface of Venus to become habitable, its temperature would need to be lowered by several hundred degrees. The solution proposed by several researchers, including Paul Birch, is to place an immense veil between Venus and the Sun at the L1 Lagrange point, a shield made of reflective materials that would shade Venus and allow it to cool progressively. Estimates suggest that with a sufficiently large shade, the surface of Venus could shed hundreds of degrees within a few centuries. The second challenge is eliminating the CO2. Cooling the planet is not enough. One must also get rid of this suffocating atmosphere. One proposed method involves introducing large quantities of magnesium or calcium dust, sourced, for example, from Mercury, which would react with the atmospheric CO2 to form solid carbonates, locking the carbon into stable rocks. Another method, proposed by Robert Zubrin, involves injecting hydrogen into the Venusian atmosphere, which would react with the CO2 to produce water and solid carbon. The third challenge is water. Unlike Mars, Venus is extraordinarily dry. Its atmosphere contains only infinitesimal traces of water vapor, the result of billions of years of evaporation and dissociation by ultraviolet rays. To create oceans on Venus, water would have to be imported from outside, probably by bombarding the planet with icy asteroids and comets. But the fourth challenge may be the strangest and most difficult to solve: rotation. Venus rotates on itself with stupefying slowness. A Venusian day lasts 243 Earth days. This means nights and days that each last several months. Half the planet burns beneath a relentless sun for weeks. The other half freezes in total darkness for the same duration. No stable seasonal cycle, no atmospheric circulation comparable to ours. Accelerating the rotation of an entire planet would require quantities of energy and engineering mechanisms that, for most researchers, exceed any realistic conception. The complete terraforming of Venus could take tens or even hundreds of millennia. And yet, there is one idea that elegantly sidesteps all these problems at once. An idea that does not seek to transform the surface of Venus, but to inhabit something no one expected to find up there. The most Earth-like location in the entire solar system, outside of Earth itself, hidden 50 kilometers up in the clouds of an infernal planet. 50 kilometers above the surface of Venus, something strange happens. The hell stops. Atmospheric pressure at that altitude is comparable to what we breathe at sea level on Earth. The temperature ranges between 20 and 30 degrees Celsius. Radiation is low, absorbed by the thick atmospheric layer below. There is light, a great deal of light, in fact, since Venus is closer to the Sun than Earth is. And although the air is unbreathable, carbon dioxide and suspended sulfuric acid, the pressure and temperature are those of a spring day on Earth. It is Jeffrey Landis, a NASA researcher and science fiction author, who put this idea into words in the 2000s. The upper atmosphere of Venus may be the most habitable place in the solar system outside of Earth itself. Not its surface, its sky. And what if, instead of terraforming Venus, we colonized it from above? Landis proposed the concept of floating cities, inflatable structures, domes filled with breathable air, that would float in the Venusian atmosphere like giant hot air balloons. The physical logic is elegant. A mixture of breathable nitrogen and oxygen is lighter than the Venusian carbon dioxide at that altitude. A dome filled with Earth-like air would float naturally in Venus's atmosphere, without needing engines or active lift, exactly like a helium balloon in Earth's air, but on an incomparably larger scale. These floating cities would offer several advantages that Mars cannot match. The gravity at Venus's surface is almost identical to Earth's gravity, about 90% of ours, which would resolve the problem of bone and muscle degeneration threatening future Martian colonists subjected to the reduced gravity of the red planet. Protection from radiation would be provided by the thick atmosphere below. Transit time from Earth is shorter than to Mars, and unlike Venus's surface, the upper atmosphere would not require a pressurized suit, only an oxygen mask to compensate for the absence of breathable air. NASA pushed this idea further with the HAVOC project, High-Altitude Venus Operational Concept. Designed to study the feasibility of a crewed mission in the upper Venusian atmosphere, HAVOC envisioned, in a first phase, the sending of robotic probes, then a short-duration human mission in orbit around Venus, then a human presence in the atmosphere, and ultimately, a permanent floating colony. NASA researchers, including Dale Arney, described the upper atmosphere of Venus as probably the closest thing to Earth in the entire solar system. A statement that surprises, but that the numbers confirm. The technical challenges remain considerable. The sulfuric acid clouds at that altitude corrode most known materials. Acid-resistant membranes must be developed for the dome walls. Supplying food, water, and energy in an environment suspended 50 kilometers up poses unprecedented engineering problems. And the flight from the surface or from orbit to these floating cities is a considerable challenge. But the idea holds. It has even gained credibility as scientific data on the Venusian atmosphere has become more precise. Scientists have even suggested that microbes might exist naturally in the clouds of Venus, a controversial hypothesis that has reignited interest in the planet. NASA selected the Da Vinci mission, expected to be launched toward the end of this decade, to precisely probe the chemical composition of the Venusian atmosphere and resolve some of these questions. What is fascinating about the vision of cities in the clouds of Venus is that it proposes planetary colonization without prior terraforming. One does not wait millennia for the surface to be transformed. One settles where conditions are already favorable, now, with technologies we can conceive of today. It is a radically different philosophy from the one that governs the terraforming of Mars, and the two approaches are not mutually exclusive. One can very well envision Venusian floating cities, while robots begin, on the surface of Mars, the first stages of a transformation that will not be completed for centuries. The question is no longer whether it is possible. The question is, when do we start? And on that, one man has very precise ideas. In May 2025, Elon Musk stood before his employees in the Star Factory in Boca Chica, Texas, and presented them with a roadmap for the next 10 years. Not to conquer a market, to conquer a planet. The plan was detailed, ambitious, and, as is often the case with Musk, accompanied by a timeline that most outside engineers found highly optimistic. 5 uncrewed starships to be launched toward Mars at the end of 2026, during the next favorable launch window. These windows only open every 26 months, when Earth's and Mars's orbits come close enough. Each of these 5 ships would carry approximately 10 tons of equipment. Their mission: to test that the starships can reach Mars, land, and survive. If these landings succeed, around 20 ships would follow in the next window of 2028 to 2029, each with a much greater payload capacity, to begin installing basic infrastructure. Tesla's Optimus robots on board, solar panels, drills, equipment to produce return fuel from the Martian atmosphere. And perhaps, if everything goes well, the first crewed missions during that same window. Musk himself publicly acknowledged that the probability of launching that first uncrewed starship toward Mars by the end of 2026 was roughly 50-50. The technical obstacles are real. Orbital refueling, filling a starship with propellant in Earth orbit from a tanker ship, has never been tested at scale, and it is a prerequisite for the vehicle to have enough energy to reach Mars. And then, in February 2026, Musk announced a delay. He pushed back his Martian ambitions by 5 to 7 years to concentrate SpaceX's resources on lunar missions within the framework of NASA's Artemis program, for which SpaceX has a multi-billion-dollar contract. Mars waits, the Moon comes first. This perfectly illustrates the gap between terraforming dreams and the reality of timelines. Even for the man most determined in the world to put humans on Mars, and who has one of the most advanced space companies in history, deadlines slip, goals get pushed back, obstacles prove more complex than anticipated. Robert Zubrin, founder of the Mars Society and one of the intellectual architects of Martian colonization, holds a longer and perhaps wiser view. For him, terraforming is not the immediate goal, it is the distant horizon. The immediate goal is to establish a permanent human presence on Mars, bases, autonomous colonies capable of locally producing their own food and energy. These colonies would be the starting point for a Martian civilization that, over generations, would accumulate the technological resources and the motivation to begin modifying its planet. Because here is what few terraforming plans account for sufficiently: the human scale of the undertaking. Even accepting that it takes 1,000 years to create a breathable atmosphere on Mars, who will maintain the effort for 1,000 years? What institutions, what motivations, what governance systems could survive across 40 human generations and continue working on the same project? Human history knows no precedent for such continuity. The pyramids took generations, certainly, but even the civilizations that built them did not last 1,000 years without radical transformation. Terraforming is not merely an engineering challenge, it is a civilizational challenge. And before even beginning to modify a planet, humanity may first need to modify itself, in how it thinks about time, how it plans, how it passes projects on to generations that do not yet have a face. Which inevitably raises another question. A question some ask with awkward embarrassment and others ask with frank anger. Do we even have the right to do this? There is a scenario that astrobiologists almost dare not voice aloud, so vertiginous would its implications be. We send our first colonists to Mars. They begin installing terraforming equipment, warming the planet, releasing gases. And there, in Martian rocks or in pockets of underground water, someone finds something. Microscopic structures, chemical signatures, traces of life, past or present. If Mars harbors microbes, even fossilized, even dormant for millions of years, terraforming that planet amounts to deliberately destroying the only other biosphere we know of in the universe. This would be, according to some researchers, the most serious ecological crime conceivable in the history of our species. A planned and knowingly executed interplanetary mass extinction. This is the heart of the ethical debate on terraforming, and it pits two radically incompatible worldviews against each other. On one side, the anthropocentrism of Robert Zubrin. For Zubrin, the expansion of life in the universe is a value in itself. Life is precious, and the more of it there is, the better. If Mars is sterile today, terraforming it is not only permitted, but morally desirable. We transform a dead rock into a living world. We increase the quantity of life in the universe. We ensure the survival of human civilization in the face of the catastrophes that could strike Earth. Zubrin goes further. According to him, leaving Mars dead when we had the means to awaken it would be a moral waste, a missed opportunity of the same nature as leaving a desert where one could have created a forest. On the other side, the biocentrism of Christopher McKay, a NASA researcher and longtime friend of Zubrin, with whom he has debated this question publicly for decades. For McKay, if Martian life exists, even microscopic, even primitive, it has an intrinsic value, independent of its usefulness to humans. Any life that emerged independently of terrestrial life would be a unique window into universal biochemistry, into the conditions for the emergence of life, and potentially into the very origins of living matter. Destroying it for human colonization would be an irreparable loss to knowledge, and perhaps a moral failing. McKay himself formulated a compromise. If Mars harbors life, one should first study it exhaustively, understand it, preserve it. And only if that Martian life were genetically and biochemically identical to terrestrial life, which would suggest a common origin, perhaps via meteorites carrying spores, Would terraforming be morally easier to defend, since we would be extending an already shared biosphere rather than destroying a separate one? But there is a third voice in this debate, often quieter, and yet perhaps the most piercing. It is the voice that says, if we are truly capable of terraforming another planet, if we have the technologies, the resources, the will, and the coordination needed to transform Mars or Venus over centuries, then why do we not start by applying all of this to Earth itself? Our planet is changing. Biodiversity is collapsing. The climate is warming. Glaciers are disappearing. Coral reefs are bleaching. Species are going extinct at a rate that has no equivalent since the end of the dinosaurs. If we had the tools to regreen deserts, to reduce greenhouse gas emissions on a large scale, to restore devastated ecosystems, should we not be using those tools here, now, on the only world where the complex life we know has managed to flourish? Under this light, terraforming ceases to be merely a question about Mars or Venus. It becomes a mirror held up to ourselves, a revealer of our priorities, of what we choose to save, of where we choose to invest our intelligence and our resources. And the answer we give to that question will perhaps say more about us than all the technology we could ever develop. There is something deeply human in the project of terraforming, something that reaches back to the first time one of our ancestors planted a seed in barren soil or diverted a stream to irrigate an arid field. We have always transformed our environment to make it habitable. That is precisely what made us the species we are. Terraforming is not a break from this history. It is its most radical extension. What we have explored in this video is not science fiction. It is science in the making. Orbital mirrors, magnetic shields, silica aerogels, genetically modified pioneer organisms, floating cities above Venus. All of this is real, studied, debated at the world's leading universities and greatest research centers. None of it is ready for tomorrow, but all of it is becoming conceivable, calculable, plannable. The terraforming of Mars or Venus will not be the work of one generation, or even 10. It will be the work of an entire civilization that will have decided the future of life should not remain confined to a single fragile planet orbiting an ordinary star in a galaxy among billions. That is a decision we are not yet in a position to make, but we are beginning, for the first time in our history, to have the tools. The question is no longer, is it possible? The question is, do we truly want it? And if so, who begins? If this video has made you want to go further, to dig deeper into the mysteries of our solar system and the great questions that science poses to our era, subscribe to the channel and leave a like. It is the best way to help us continue this work. And if you would like to directly support the channel, you will find a link in the description to make a donation, even a modest one. Every contribution allows us to produce richer and more thoroughly researched videos. Tell us in the comments which city you are watching from right now and what time it is where you are.